All right. Okay. So again, thanks for the invitation. Great to be here. Especially nice because there are a number of people here that I seem to have known forever, but haven't seen much in recent years. So it's great to see everybody again. So really, what I want to do in this talk is really show you the details of one specific example of something. So, I mean, why do that? So, because I think it turns out there's quite a lot of very pretty geometry in this example that is nice to see, and hopefully it sort of illustrates some tools and techniques that will have use beyond this example. Let me give you the setup. And tell you what the example is. So we're starting with a closed-oriented surface, that's sigma, genus G, and a Lie group, big G, which at this point can be anything. And so associated to these, a Riemann surface and a group, and this is a well-known story, there are sort of three fundamental moduli spaces associated to this, or if you prefer, sort of three avatars of one space. So the first one, which requires just topological information about the surface and the group, I guess I should have used that board first, is the space of representations of the fundamental group of the surface into G. This means space of homomorphisms up to conjugation. The second one, which requires adding smooth structure to the picture, is the moduli space of flat G bundles on sigma. The relation between these comes in this direction from holonomy representation, and that's enough to say about that at this stage. And then the third space you get if you add complex structure to the Riemann surface, and then this becomes the modular space of G Higgs bundles. And the correspondence between these two relies on two big results due to Corlett and version Donaldson, and a correspondence known as Hitchin-Kobayashi correspondence, due in this setting to Hitchin and Simpson. So there are these three, and the relation between them is, of course, a very rich and interesting subject. What I want to focus on here is, so what happens, so you have this for any, let's say, reductive group G. So suppose you have two groups related by a group homomorphism. So then in this situation, so you can see most easily over here on this end that representations into G1 can compose with psi, and that will give you a map to the representation variety for representations into G2. And so you'll get similarly correspondences for all of these, and this is the one that I want to concentrate on. What this relation between the moduli space of Higgs bundles for different groups will look like for specific relation between G1 and G2. So this is where the story is going to be set. I'm not going to talk about this in great generality. I'm going to look at a specific situation where the relation between these two groups is an isogeny, so the one is just a finite cover of the other, and in fact I want to look at a situation where this comes from an isomorphism, one of these exceptional isomorphisms between low-dimensional Lie algebras. Again, even more specifically, I want to look, so in this talk I'll really only talk about one just because of time constraints, I want to look at the relation between SL4 and SO6. But if you like, you can think of this as one of the low-dimensional isomorphisms relating to the special orthogonal groups. The others are also very interesting. This is the relation between the symplectic group and SO5, and then for SL4, haven't left notice space. For SO4, the isomorphism is from SL2C cross SL2C. So I want to look at these, and also I want to try and find time to say something about the induced relationships on some of the real forms of these complex groups, and in particular the split real forms. So in this case, that's the group SL4R, and the split real form for this guy is SO33. So special orthogonal group signature 3,3, and actually I should get put a little 0 there. Connected group. Okay, so I'm going to talk about this guy and this one, and I want to see what they have to say about that part. So, there's sort of several points of interest reflected on what I've put on the board here already. In general, if you look at the locus in the modular space of Higgs bundles for a complex group of the Higgs bundles that correspond to representations into a real form, that defines an interesting locus inside here. It reminds me, I should have said right at the beginning that everything that I'm going to tell you, the work that that's not classical that I'm going to tell you about is joint with Laura Shapoznik. Sorry, Laura, I should have said that right at the beginning. These loci of the real Higgs bundles sitting inside the complex Higgs bundles turn out to form interesting objects. They're actually examples of what are called BAA branes. Several of these groups have special interest. The split real form here is SL2R cross SL2R, and SL2R plays a very special role because of its relation to Teichmuller space. There are other interesting groups. The split real form of this is SO22, and that's the isometry group of an interesting space 2, anti-de Sitter space. Let's see the other. This SL4R is a group that us who grew up with gauge theory in 4 dimensions know well. There's lots of special geometry in 4 dimensions that will appear when we talk about this. This correspondence is actually a relation of a group with its Langland's dual, so there's some interest there. And then finally this one, this relation with SL4 and SO6 relates to a construction in algebraic geometry in the theory of prim varieties. That was a pleasant discovery to find that what we were doing had some relation to something as pretty as that. And I'll tell you something about that as we go along. This is a construction due to Rassilus. I'm not sure I'm pronouncing the name correctly. Okay, so that's sort of the introduction. So first thing I have to do is tell you something about the objects that we want to relate, the Higgs bundles. And I want to describe these in 2 different ways and look at the relationship in both of these ways. So these 2 ways, one is sort of a vector bundle point of view, and the other is a spectral curves point of view. Let me start. Talking about Higgs bundles sort of described in terms of vector bundles. So these are all Higgs bundles, let me remind you, on our surface sigma. And actually, if we're talking about Higgs bundles, I should maybe just remind you that we fixed a complex structure there. So it's not just a topological surface, but a Riemann surface. So Higgs bundles, whatever else they are holomorphic bundles with an extra piece of datum that's the Higgs field. These can be defined for any group G there corresponding to these representations. And the way the data looks depends on the group. But let me just tell you for the cases that we're interested in. So first of all, for SLN, so for these, what is a Higgs bundle? So it consists of a rank n holomorphic bundle over sigma, and the S here tells you that the determinant of the bundle is trivial, and the Higgs field is a holomorphic map from V to V twisted by the canonical bundle on sigma. So you can think of it as a section of an associated bundle, the endomorphism bundle. It has a one-form nature, so twisted by the canonical bundle, and the S here influences this because it means that the trace of this has to be 0. So that's all an SLNC Higgs bundle is, a rank n bundle together with a holomorphic section of this associated bundle. For the spatial orthogonal groups, we're interested in the ones in SO2n, although the 2 at this stage isn't going to matter. So these, again, you can think of as a vector bundle and a Higgs field, but now there are extra constraints reflecting the fact that the group is SO2n, reflecting the fact that the correspondence over here has to give you things with holonomy in SO2n. And the extra conditions are that the bundle has to have an orthogonal structure. So there's a symmetric bilinear form, or you can think of it as a symmetric map from V to its dual. You also actually have to fix the identification of the determinant with the so it's got a trivial determinant, but the trivialization is actually part of the data here. The extra condition on the Higgs field to get it into the Lie algebra of SO2n is that it should be skew with respect to Q. So I'll say it's Q skew. Just summarizing briefly what this looks like. Okay, so before I get to the spectral data picture, let me just sort of highlight some of the points of interest about these Higgs bundles and their moduli spaces. So for these objects, and actually for any group, there is a notion of stability that allows you to define a moduli space for these, a moduli space for fixed topological type. So you don't need to know exactly what the condition looks like. It's just that there is this condition which leads to the construction of these moduli spaces. The second, and so there's many things we could talk for months about these, but I'm going to just sort of focus on what I need for this story. So one of the things is that, so the Higgs fields, you can see from this description, in a local frame for V are just matrices with values in one forms. So phi is, so it's locally a matrix of one forms, but I mean the matrix depends on the local frame. On the other hand, if you take any invariant polynomial invariant under the action of the group on the Lie algebra, that will be insensitive to gauge transformations, and so you can evaluate an invariant polynomial on this and get a globally well-defined object. So for any invariant polynomials B, if you evaluate that on the Higgs field, that makes sense. If this is a degree D polynomial, then the result will be a D form. So this will be a section of the D power of the canonical bundle. So if you take all of them, all the invariant polynomials, or in particular a basis for the ring of invariant polynomials generating set, then you can evaluate that on all the Higgs fields, and that will give you a map to the combined space where all of them live. So it will be the sum over these spaces of sections of powers of the canonical bundle, where di is the degree of the polynomial, and we've used here a generating set for the ring of invariant polynomials. So this map, this is the Hitchin vibration, fibers the moduli space over this vector space consisting of all these spaces of sections. The fibers we'll see in the cases we're interested in, and turn out to be abelian varieties, and this is where the integrable system, Hitchin integrable system, is defined. So this is sort of a central player in modulus in Higgs bundle stories. Okay, so that's the vector description. It's meant to be so resistant.
I think if you press in the middle, it's not as hard.
Okay, so there is this alternative way of encoding the information that defines the Higgs field in terms of spectral data. So among the reasons for doing this are, as we'll see, it gives you a really good way of understanding the fibers of this vibration. It also, not in all cases, but in many cases, gives you a sort of an abelianization of the picture, meaning that you trade in vector bundles of rank n for line bundles. Okay, so what is this alternative view? Spectral data. So here we're going to replace the vector bundle and a Higgs field, whatever defining properties are, with a new curve and a line bundle. So this is going to be the spectral curve, and this is going to be a line bundle on the spectral curve. So we need to code in bits. So where do these come from? So the curve, so this you can think of as being defined by the characteristic polynomial for lambda. So that's the roots, for phi. So it's the roots of this lambda, so a formal variable. So this, the solution to this, there are in general n roots of these. These define the eigenvalues of phi. But so if you think of the solution to this as a multi-valued function with n values giving the eigenvalues, then the curve S is the curve on which the solution to this becomes a single-valued function. So this is sort of going all the way back to the original way Riemann surfaces were defined. So this is the curve on which the eigenvalue function, or the root of the characteristic polynomial is single valued. So formally, this curve because this has a one-form nature to it, it's not just a matrix, this curve lives inside the total space of the canonical bundle. So this is the canonical bundle over sigma. Over this, you can pull the canonical bundle back to its total space. I call that projection pi. Then the lambda is the tautological section of this bundle. So its value over a point here is the one form determined by that point. And this equation then defines a locus in here. That's where S sits. So this is in general an n-to-1, an n-fold covering. Ramified, of course, but an n-fold covering. Okay, so that's the spectral curve. The line bundle, called U over there. So this is line bundle on S. Its relation to the vector bundle V is meant to be that you recover V by taking the direct image of this under the projection. So if this is an n-to-1 covering, then the direct image will be a rank n bundle. But the bundle has to satisfy the appropriate conditions for whatever group Higgs bundle we're talking about. And so those are reflected in conditions on U. So it's not any bundle in the Jacobian. It's the appropriate one to recover the conditions on V. And the Higgs field is recovered, I should just mention here, from the variable lambda thought of as a map from U to U twisted in here to the pullback of the canonical bundle. When you push that forward under this direct image, that recovers phi. So what do you get in the cases that we are interested in? And actually, maybe I'll put those.
Just to put this on a common footing, so you could say that U is the eigenspaces of.
Exactly. Right. So. Right, and all that makes it's all much more transparent over the generic point away from ramification points where the eigenvalues are all distinct. But the machinery sort of takes care of what happens over the branch locus as well. Okay, so the situations that we're interested in are SLN, in fact SL4, but here it really doesn't matter to be a little bit more general, and SO2N, in fact SO6. So for these, what does the spectral data look like? So the spectral curve is defined by the characteristic equation for a matrix in the Lie algebra of SLN, and so that's anything of this form. The only constraint on the polynomial here is that the n minus first term has a zero coefficient reflecting the vanishing trace, but otherwise anything goes. The AI here are differentials in k to the I. So that's the polynomial that defines the spectral curve. For generic choices of these, so these are now coordinates in the base of pitch and vibration. Generically, the curve will be smooth, but not always. So there will be a singular locus. This, let's just say, generically smooth. And the constraint on the line bundle U is determined by the requirement that its determinant has to be trivial. And so what that means is that not exactly U, but U twisted by something that encodes information at the ramification divisors. So U twisted by so this R is the ramification divisor for the covering. And the condition is that this guy has to be in the prim variety for this cover. So that means it has to be in the kernel of the norm map-on divisors from there to there. So I'll just leave it like that. So that's the constraint, and let's give that a name. On the bundle that will give you an SLNC Higgs bundle, the spectral data is usually given as a pair, the spectral curve and the bundle in the prim variety, showing you that the fibers of the Higgs vibration in this case are these abelian varieties. For SO2NC, the spectral data is a little bit more intricate. First of all, the characteristic polynomial for something coming from this group only has even powers. And in the last coefficient, the fact that we're talking about SO2n comes into play. The last coefficient is a square. This is actually the Pfaffian of this guy squared. So the square of the Pfaffian is the determinant. This has to be the determinant, but in even orthogonal groups, that's the square of something. In this case, so because of this square, this has the consequence that the spectral curve for any choice of these is always singular. That's the bad news. The good news is that it comes with an involution. You can see lambda goes to minus lambda is an involution on this curve. So it has this extra symmetry. So the spectral curve is actually the desingularization of this. Which for generic choices of the points will be smooth. This is the desingularization. The involution lifts to this desingularization, where in fact it is fixed point free. So this is a curve with an involution, and the quotient is again generically a nice smooth curve. So you get the desingularization, and you can quotient that. Let's use sigma for the involution here, for the projection under the involution. This guy is a 2n-fold cover of the original curve. This guy, when you quotient it out by this involution, is now an n-fold cover of the curve. And the condition on the line bundle, in order that the projection has the properties that an SO2NC Higgs bundle is meant to have, namely that it has an orthogonal structure. The implication of this is that again the bundle U that's in the Jacobian twisted by a ramification divisor. I'll call it R hat because it's now the ramification divisor in the desingularization to the minus a half. Again, should be in a prim variety. This time it's the prim variety for this covering.
Should I think of S hat as living within total space of a square root of the current covering?
No, I mean it's closer to thinking of it as living in the square, and I'll show you in the construction that I'm going to give you for how to understand this in this particular case. You'll see explicitly where it lives. It actually doesn't live in a line bundle, but lives in some. I'll show you. So this has to lie in this prim. So this is the model for the fiber of the Higgs vibration in the SO2NC case. Okay. So what I want to do is show you how these descriptions of the Higgs bundles get related by the specific isogeny that relates SO4, SL4, and SO6. So let me. Sorry, any other questions about this before we move on to that? Please don't hold back. Okay, so the isogeny relating SO4 to SO6. So there's several ways to see it. One nice way is to this is the six-dimensional representation of SL4 on the six-dimensional space that you get by taking wedge 2 of C4. And so what this means is that I call that psi. So if I give you a matrix in SL4, its image in this is wedge 2 of the matrix, by which I mean the tensor product restricted to wedge 2. So that's all the map is. Because we also need to know what happens to Higgs fields, which live in the Lie algebra, you also need to know what the derivative of this is at the identity. And this is, it's really just the derivative of this map. So it looks like that. I mean, so the most tricky thing about this is to understand why this image is in SO, not just SL. So where does the orthogonal structure come from in this construction? And the orthogonal structure so remember we're starting out with an SL4, so we're starting out with a matrices with fixed determinant. So we feed that into this general relation. So this applies to any vector space. But here, so we have wedge K of Cn, wedge N Cn dual. So okay, let me put a V. It sort of seems a bit artificial to put this, because this really applies to any vector space. The isomorphism, there's an isomorphism from K forms on V, N forms on V dual to N minus KV, which comes by taking sort of interior product with a volume form there. N minus K, thanks.
N is the dimension of the...
And right, so N is the dimension of V, which in our case is 4, K in our case is 2, and we feed into this the fact that we have an identification with C. So if you feed that in, then this isomorphism is a map from this space to, sorry.
More directly, you could just wedge the thing with itself.
Sorry?
Given an element of lambda 2, you can wedge it with itself, you get an element of lambda 4, and then that's been trivialized. So that's the question.
Okay, sure. You can write it that way too. And the point is that you're feeding in the trivialization here. So when you do this on a bundle, you need the trivialization of the bundle in order to get the map from the vector space to its dual, from the bundle to its dual. Okay, so
this is a Hodge star rather than the Hodge.
we'll get to that. There's no Hodge star yet, because this is
Algebraically, this is how you construct a Hodge star.
well, you need one more piece of information, which I'll tell you about in a minute, because this is only in SL. then Hodge-star needs a metric, right? And, so we'll get
Oh,
to
yeah,
that.
well, you sort of have to, sorry, but you have to then identify the vector spaces to it.
Well, that's you're thinking in the right way. Okay, so all right, so what does this do to the Higgs bundles? So the first one is fairly straightforward. So if we look at the map from the vector bundle description of SL4 to SO6, so here we're going from a rank 4 trivial determinant with a Higgs field in SL4, and we have to produce, so this is rank 4 with the other conditions. We have to produce a rank 6, I better give it a different name from V, with its Higgs field that lives in the algebra of SL6, I'll give that a different name. And this has to have an orthogonal structure, and phi has to have the appropriate symmetry. So here, this is a bundle associated, the structure group is SL4. This is the bundle structure group is SO6, the bundle related by this transformation. So W is wedge to a V in this situation. The trivialization of V induces the orthogonal structure on W in the way that isomorphism shows. And the Higgs field is the just the derivative map of psi applied to phi. So these and other isomorphisms of this sort, several of them were worked out in the thesis of Marta Arroyo, who was a student of Oscar Garcia Prades, and there's a lot of nice information in her thesis about these things. One thing that's not spelled out there, though, is what happens if you restrict this to the Higgs bundles that correspond to the split real form. And that's a pretty story that involves, as Claude has already predicted, something like a Hodge-star. So let me just take a few minutes to tell you that. So restricted to SL4. So this is one of the real forms of SL4C, in fact, the split real form. So in this situation, the extra structure that the Higgs bundle, the V phi, has is that V acquires an orthogonal structure, and the Higgs field also has a specific form, but let's just focus for a moment on that. V has its own orthogonal structure. So you can think of that as an isomorphism of V with its dual, or you can think of it as a symmetric bilinear product on V tensor V. So the output, so this is the extra information on that side. The output over here is going to be an SO3 Higgs bundle, which means that the bundle over there has to, so I guess I didn't tell you what these look like. Sorry guys, I realize I skipped a part of the story. How do you know what the Higgs bundle, what the extra restrictions for these Higgs bundles with the corresponding to the real form should be? So, I mean, one way to think about it is through the correspondence with the representation variety. You want the information in the Higgs bundle to be such that under this correspondence, they give you a flat connection whose holonomy is in the real form rather than the full complex group. And that's one way to understand what the restrictions are. In this case, it boils down to the bundle having an orthogonal structure and the Higgs field having a particular shape. In this case, it boils down to the bundle having its structure group reduce. In all cases, it's always the bundle structure group reduces to the maximal compact subgroup of the in this case it's SO3 times SO3. So that means this splits into two rank 3 bundles, each of which has its own orthogonal form. So how do you see that coming out of this picture? And so here's where the Hodge star enters, because if we have this Q, now we have this Q, which induces an orthogonal structure on wedge 2, and you can combine those so that's so the notation here, it's not exactly that Q, right? It's the induced one. This combination is an involution that I'm going to call star for obvious reasons. This is the Hodge star if this is wedge 2 of the tangent bundle on the 4-dimensional manifold. This involution defined by a combination of these decomposes the bundle into the isotypic parts, the +1 eigenspace and the -1 eigenspace. And that's exactly what is underlying this map on the Higgs bundles. This decomposition and the existence of this star is a manifestation of the fact that SO4 is not a simple group, and it has 2 SO3 normal subgroups. This here is a reduction of the structure group from SO4 to SO3 cross SO3, and those 2 SO3s are exactly the normal subgroups. So that whole story is reflected in this map over here. Okay, so let me tell you something about the spectral curves.
I got a bit lost. Might take several months.
Sorry, that wasn't the intention.
These are of the same original surface, is this right? I got a bit confused with the spectral curve was a cover of the original surface,
Right.
and
The spectral
this
curve
V-
hasn't entered
but
yet.
you haven't mentioned that. So, but this V and W are over the original surface.
Right.
They're a different rank, and this is an explicit construction mapping
Mapping a
something on V and on
it's mapping the rank 4 bundle and Higgs field.
to W, from V to W.
Right.
Through this, the basic formula is this, the one halfway down on the left, this D psi.
That's the one that was used here.
Yeah. And is this the adjoint? Is it the same as the adjoint? I mean, I know I answered SL2 and SO3. How different is this? Is it also 2 to 1, and is it?
That map?
Yeah.
Yeah. I mean, in fact, SL4 is spin SO.
Right.
SO6.
Is it just the adjoint map?
What do you mean?
What's the adjoint representation
if you
of
just think
SL4?
of- If you just think, if you think of V as having some indices alpha, and then W would have alpha beta, 2 skew indices,
Right.
and then this map is something where you have a Kronecker delta times.
You want to know what this map is?
It is adjoint representation.
Thank you.
Yeah. Okay. All right. So, what happens to the spectral curves? I wanted to do this. That'll save rewriting some of the spectral curve information. Okay, so we want the map that takes a spectral curve for SL4. I'll call that S4. So this is a 4-to-1 cover of our original curve. Projection is called that pi4, and we have to get out of this spectral curve for SO6, and really what we want is the desingularization of that. So that's what this notation will mean. It's going to be the spectral desingularization of the curve defined by the characteristic of get to something I may not get to. So this is a 4-to-1 cover. This is a 6-fold cover. So this projection is pi 6 hat. It's a curve which has an involution. So it's quotient by the involution that I mentioned over there. This is a 3-fold cover. So the relation that we're going to get is a relation between a 4-fold cover and a 6-fold cover with an involution. And this is exactly the correspondence that is described by the construction due to Russellis. It's known as Russellis' trigonal construction. This relation between 4-fold, and this leads to a relation between prim varieties, which I'll get to. So we're in, turns out, a sort of a fairly familiar setting, but we're going to have a new bundle point of view on it. Okay, so how do we get, given this curve, how do we get that curve?
There's a point.
Sorry?
Pairs of.
Yeah, I think you're thinking along the right way.
Right.
So here's,
Two pairs of points in.
you mean that's what this one is?
Yeah.
Yeah. So, okay, so here's a sort of a low-tech way to think about how to get this curve from that curve. So the low-tech recipe is based on these observations. So first of all, what are the fibers of these maps? For any spectral curve that's representing a Higgs bundle, the fiber of the projection gives you the eigenvalues of the Higgs field. That's by the way they constructed. So that's the first thing. The second thing is that under the map on Higgs fields, which comes from the derivative of this, what happens to the eigenvalues? And the key thing is that under that map, which is gone, the eigenvalues add. Look at the derivative of this map. If the S4 curve is defined by the polynomial written in terms of its eigenvalues like that, then the curve for the spectral, the curve defining the spectral curve out of which X6 is constructed has to be given at least heuristically by its eigenvalues, and the eigenvalues here are going to be the sums of the eigenvalues there. So I'll write it now with 2 indices. Let's call them mu's instead of lambdas. So these are the eigenvalues of the roots of this polynomial. This is for distinct pairs of i's and j's. And so here, mu I j is lambda I plus lambda j. And then you calculate and you see how the coefficients of this equation are related to the coefficients of that equation.
So the involution is you replace a pair of points with its complement.
Exactly. Okay. You have to work harder to trick you up, I can see. Okay, so this out of this, this is enough information to see what happens to the points in the Hitchin base for these 2 vibrations. Described with respect to specific bases for the ring of invariant polynomials, but I think I won't write down the formulas, but you get it. So that's one way of thinking about it. Notice though that this gives you the singular curve, not the S6 directly. And also this doesn't, there's still a bit of a leap from this to what happens to the line bundle part of the spectral data. So let me show you the other way of constructing this map. That will address both of those. So let me do this in a couple of steps. So the first one is, okay, so we start with our spectral curve for the SL4. Out of this, we construct the fiber product of the curve with itself. So that's step one. So this is the fiber product that laser points over the same base. So this curve, because we've taken the fiber product of the curve with itself, always has at least two components. It has a diagonally embedded copy of S4 and then another component. The other component is the one that we're interested in. So let's right away remove the diagonal. And take the other component, which I'll just call this with a little 0. And for generic choices of S's, meaning generic points in the base of the Hitchin vibration, for this, this will be smooth and irreducible. So that's the first stage of the construction. So we take that. This curve has symmetry, interchanging the two factors. We want to, the next step is to absorb that symmetry, in other words, quotient by it, we'll call it tau. So that would give us a curve quotiented like that. So where does this live? So this curve, this lives inside the total space of the canonical bundle. So this curve lives inside the total space of the canonical bundle with itself. So this quotient lives inside the quotient. So this is like the second symmetric product of.
I'm sorry, I'm a bit confused. You've taken. I presume you're going up to symmetric products. You'd be taking you have a complex surface for the fibers, right?
It's the fiber product. So I'm not taking the full symmetric product. I'm only taking points that lie with the same fiber.
Oh, I see.
That's what the little subscript there means.
Yeah, right.
Okay. So that's why it's really in the total space of this bundle. So this guy lives in the quotient of this. So this is like the second symmetric product of C2, which you know, this is the fact that tells you that symmetric products of Riemann surfaces are actually smooth. You can transform that into k plus k squared. This is the map that replaces roots with coefficients of polynomials, or is it the other way around? I'm not sure, but it's the map that takes an unordered pair to the sum and the product. And it's sometimes more convenient to view the curve as sitting inside there. So under this map, this is the curve that I'm claiming is the curve that we want. And generically, this is smooth. So this may be as a proposition that the properties that this curve has is generically, this curve is smooth. If you look at its projection onto here, so if you take its projection into here, now you have a curve that lives inside the total space of the canonical bundle, and that is exactly the curve defined by that equation. So its projection onto K is the spectral curve for the SO6. So if you wanted to understand really what this curve looks like, it's what I think Claude was alluding to. If you look at a generic fiber, so away from the branch locus of the covering of this curve over sigma, the fiber of S4 has 4 points. Let's call them A, B, C, D. This is in S4. The fiber of this curve is all the unordered pairs of these. So there's 6 of them, and that are all the unordered pairs. So that's, I mean, you can trace through what this construction will give you, and that's exactly what it is. The involution on this is, so here we have 4 points. So if I give you one disordered pair, then there's the complementary pair. And that's the involution. So sigma of AB is CD. So this, let's see, what else did I need to tell you about this? Okay.
You're saying S6 is the quotient of this S6 out by sigma.
No, S6 is the projection of this into K. So this is a curve that's sitting in the total space of K plus K squared.
Okay, so that's not the curve.
From this point of view, it's the curve defined by this polynomial.
I'm a bit confused by some detail. I mean, didn't you say that P6 was symmetric? Involved even powers of lambda only?
This guy, yeah.
No, up there. I mean, in this low-tech version.
Oh, right. So you mean if you expand this out, how do you get that? Well, so I mean, you get that because the lambdas here are from an SL4 Higgs bundle, so the sum of the lambdas is 0.
The sum of them is 0.
Yeah. So that gives you only even terms there. So here A plus B plus C is 0. So in fact, that following that shows you that when you put this in terms of these variables, this does in fact correspond to lambda going to minus lambda, where lambda is now the variable in the equation for this guy. Okay, so unfortunately I didn't get to the how you see the map on the line bundle, but I'll just say quickly that it's basically sort of an obvious construction from here. If you start with a line bundle on S4, so this is where the spectral data for the SL4 lives, then you can pull this back to the product. You can pull it back from both ways and tensor both of those. That gives you a bundle over here, which is actually invariant under the symmetries of this. And so that actually comes from a bundle on the quotient of that by its symmetry. And that gives you the map. So then you have to show that that actually takes a bundle with the right properties for an SL4 to a bundle with the right properties for an SO6, which it does. And in fact, it's the, I mean, you can view that map in exactly the way that it appears in this Racillus construction, but I'm sorry that we never got to that. Okay.
Any questions?
Yeah.
These moduli spaces of Higgs bundles have S1 actions, and we know that
Right.
the fixed points of these S1 actions, which happen to be Higgs bundles with nilpotent Higgs fields, determine the cohomologies of the spaces. And this map here, it's from the low-tech version. It sends nilpotent Higgs bundles to nilpotent Higgs bundles because the eigenvalues add. So if they have all 0 eigenvalues, it'll go to one with all 0 eigenvalues. So does that maybe induce an injective map on cohomology?
Well, so remember that this only applies to Higgs bundles in the generic fibers of the vibration. So
this is off completely off the nilpotent.
Right. So more work would be required to answer a question like that. Yeah.
Composing the Higgs fields with projections to latitude plus, latitude give you two completely separate spectral curves, which are threefold covers. I'm just wondering if there's any.
And they would be.
I mean, your
So each
each
one-
Higgs field doesn't have to be block diagonal, but still, if you compose with projections, you're getting
It might be
maps
something
from which two
something
plus to which
interesting.
two plus. And which two minus.
Possibly so. And what kind of Higgs bundle would that be? So the symmetry that the Higgs field part that you take would have would not necessarily make it an SO3 Higgs bundle. I think maybe just be an SL3 Higgs bundle with some special property. But yeah, I don't know.
But it's weird. You just have
possibly.
two extra curves sitting there that are not terribly well related to the big six-fold cover.
Yeah, that's we haven't.
You're killing
we
some
have-
off-diagonal blocks, but it's sort of
Right, we haven't figured that out. I mean, there's actually other information here that's so far going to waste, which is that, I mean, if you take the tensor product of the SO4 Higgs bundle with itself, so that's now a rank 16 bundle. And we've used a rank 6 part of that. It comes from the exterior product. But there is also the symmetric product. And that, so that's now a rank 10 thing. I mean, that also has sort of, representation theoretic descriptions, and there might be interesting things to say about that too. The spectral curve picture for that is a little bit more intricate because for that one, you cannot throw away the diagonal in the final product. The bundle that you get is now supported partly on the diagonal and partly on the other component. So you're into just, yeah.
So I guess this construction is going to give you entire connected components of the moduli space of Higgs bundles for SO6, but are there other connected components in the moduli space that don't arise from, because this is like taking a spin structure.
Exactly, and that's exactly what determines, I mean, there are topological constraints on which components you can see, and that's even more pronounced if you look at the real forms, because there the modular space for Higgs bundles associated with real forms generally have multiple components. And under this construction, you only see half of them. And it's the explanations in terms of spin structures.
Just historical maybe, but for moduli space of just stable SL4C bundles and stable SO6C without any Higgs fields, is this well understood?
The relation
Between the two moduli spaces?
So that corresponds to Higgs fields being 0.
Yeah. Or more generally, if I have a misogyny between two groups, I have the moduli spaces of G bundles.
Yeah,
and G
sorry,
prime
I'm
bundles.
not coming up with anything on the spot here. Let me think about that.
Okay, anything else?